All right. Going here. Yeah. Morning. So, a couple things before we start out. Finish up talking about fixed effects today. Uh, we'll basically be doing a lot of work in that do file. Not a lot of slides to cover here today. I might do some review of some of the sample questions that I posted, which some of these will be things we haven't talked about yet. So it's going to be for that final quiz, which will be what we covered this week, but then also that first week after we get back from Thanksgiving break. So about half the questions will look like things we haven't talked about. But if you want to kind of start taking a look at what those questions will look like, I kind of got that question last class. You can start doing that. That quiz won't be posted until after break, but you can kind of start working on questions that look similar to what the material that we've covered this week. A couple things I'll note: those problem set 5 should be graded by the time we get back from break. Once again, I'm having my GA help me with those, but some of those grades I'll start getting up there even as early as tomorrow. Just looking at the grade book, one thing I would try to stress, and I guess at this point it's maybe falling on deaf ears, I'm seeing a lot more zeros, people just not doing these problem sets and these quizzes. They account for a pretty large percent of your grade. Those zeros are going to start to pull your average down a lot in those categories, and it's going to have some pretty big impacts on your grade. So do not dismiss these quizzes and problem sets. If you have missed some up to this point, it's even more important and crucial that you do the remaining ones. Okay. So we're going to have one more quiz and one more problem set that'll be kind of after Thanksgiving break. I will probably post the 6 problem set tomorrow. It will, obviously half of it we will have covered yet, so it's not like you'll be able to complete it, or likely you'll be able to complete it based off we haven't covered the material yet. But if you want to get an early start on it, when I'm getting emails the day that the problem set is due about questions 1 and 2, that's not a good sign. Starting at the day it's due, probably not going to be sufficient time. I've tried to stress starting these early is really, really important. Okay. So I'll get that 6 problem set up there tomorrow. The due date will be far off in the future, but just in case you want to start working on it, if you have some time before break starts or during break, kind of, depending on what your schedule looks like, you'll see that pop up as well. These are under the files tab, so you might have noticed them, but I didn't put them on the main homepage. They now should be published. I've also got a set of a practice final exam, right? So a set of questions that'll look like very similar to what your final exam will look like. I would, once again, not wait until the last minute to start reviewing these. You could start reviewing these pretty early and getting it to 3.5 weeks in advance, technically almost 4 weeks of when that final exam will be. But here's kind of the formula sheet that you'll have in the final, and then a set of questions that would be really good to be able to provide a solution. So not just look through them, but provide a solution as to why the correct answer is what it is, right? So I give you an answer key in the question. I tell my freshmen, like, if you're going through a practice exam, it doesn't mean simply sit down, take it, and kind of, oh, this is about what I get in the exam. You really need to think through each question. What would a solution be as to why the correct answer is what it is? And that's how I would use those practice exams to study. Okay. Other than that, any questions for me before we start material here today? So one other thing I will mention, and I'll mention this closer to the date as well, but I did just get an email yesterday. I saw it this morning. Our final exam, it's in the syllabus. I think that it's like around noon when it starts. So we're all the way back here. Yeah, so it's 12:40 to 2:40 on that Tuesday of finals week. The room location will be right here. So that makes it easy for us. When we lucked out and got the same room, sometimes we get thrown around, campus. We'll be in the same room as we typically will be for that final exam. So I didn't have a location attached to it in the syllabus because they don't let me know that early in the semester. I now have got confirmation we'll be in this room. Okay. All right. So that should be all the housekeeping stuff. Unless there's any questions, we'll kind of dive in where we left off. All right, so when I say dive in where we left off, I'm going to publish this in-class quiz today, and we'll kind of start with it. So there'll be a little bit of review, right? but also kind of what some questions look like. So today's code is what, 80.37. So I think not including the current problem set, this is the average or the mean grade in the class right now. So 80.37 will be the code that gets you into that in-class quiz. And then I've got the due date set to be 2:45, so 20 minutes. Once again, I'm going to use some of these questions for review, so we might take a little bit longer, but we should be done well in advance of that due date, okay? Or I should say due time, right? So we'll go back here. Everyone able to get into that quiz okay? All right. Okay. So for this first question, let's start to think about what we're doing with fixed effects. Okay. So we've got a question about what's going to happen to the R squared and what's going to happen to the adjusted R squared. So I alluded to this a little bit last class, but I really didn't dive as deep into it as I wanted to. But if we think about what we're doing with fixed effects, we said, I want to understand the relationship that exists between an X and a Y variable. So it looks very similar to a simple linear regression, but our observations are going to be from the same subjects, and we're going to have multiple periods in time. So like one person, if they showed up in the data set 5 different years, could be 5 different data points, right? So subject I and time period T. When I include fixed effects, I've got the same regression, but if I wanted to include subject level or like individual fixed effects here, so maybe my example is something like student test score data, and I might want to know what is the impact of, I think we did grade size last class, right? Well, if I want to include a control for every single student, because we all have innate abilities that I can't observe in the data, right? But I want to hold those things constant. That's a lot of omitted variable bias that could exist, right? So when I include fixed effects, really what I'm doing is I'm including a dummy variable for person 1, for person 2, etc. Except that, just like every other categorical variable, how many dummy variables will I have?
1 less.
1 less. So it wouldn't really be n minus 1, n being the number of observations in the data set. But whatever the number of subjects I have, I would have that minus 1 dummy variables. Okay. Well, if I've included a bunch of dummy variables that are attempting to control for all these innate differences across students that I can't observe, or these omitted variables that I'm now controlling for, what should happen to my R squared? So if my R squared is 1 minus the proportion that I what? Can't explain. By including these dummy variables, what should happen to my R squared? Anytime I include additional variables on the right-hand side, my R squared itself should increase. I'm going to be able to explain, even if it's minimal, some additional variation in that Y variable. Now, here's where it gets a little bit tricky, right? So if I'm thinking about my adjusted R squared, we have the same kind of equation as our R squared. So it's 1 minus the proportion we can't explain, but we scaled that proportion we couldn't explain by the number of observations minus 1 over the number of observations minus the number of independent or right-hand side variables we included, minus 1. I don't know if I said that, right? So it's not quite as clear what's going to happen to our adjusted R squared. I think I talked through last class that one thing that will happen is that we know that it's going to be negatively impacted how. So if I include more variables on the right-hand side, what's going to change here? K is going to go up. Subtracting a larger value, this denominator is going to go down. Dividing by a smaller number, my scaling factor would go up. Subtracting a larger value, my adjusted R squared is going to go down. So we said the fact that we're using fixed effects, let's assume that when I include these fixed effects, they didn't really capture any important omitted variables. So they're going to have a negative impact from the pure fact that I included them. What am I hoping for when I include additional controls? I'm hoping that the proportion that I can't explain goes down. No, right? I want the proportion I can explain to go up. But when we're thinking about this form, the proportion I can't explain, I hope that that goes down. So if these fixed effects don't matter, when this proportion I can explain, or can't explain, sorry, goes down, if I'm subtracting a smaller value, what should happen to my R squared? It should go up. But if it only goes up by a very small amount, which of these is larger is what's going to determine what happens to my adjusted R squared. So I try to draw it to scale. If my variables don't explain that much more of the variation, that's not going to cause my adjusted R squared to go up very much. The fact that I had to include all these dummy variables for every single individual, every single subject, that's going to cause my R squared to go down by quite a bit. Kind of thinking about the total effect here would be that my adjusted R squared would decrease, right? I try to draw the arrow larger here, right? Now, what if, probably more likely the case in most scenarios where we use fixed effects, if I'm controlling for the student and that captures a lot of things I can't observe, what is likely to happen to the proportion I can't explain? It's going to go down a lot, right? I can now explain a lot more of that variation because I'm controlling for these factors that are constant within this individual across time. So what's more likely to happen is when I include these, yes, it still has that negative impact because I had to include more variables, but that proportion I can't explain is going to go down a lot. If I'm subtracting a much larger value, my adjusted R squared would then increase by a lot. And that increase will more than compensate for the fact that I had to include additional control variables, right? So more likely the case is that my adjusted R squared is going to go, what would the total effect in the second scenario be? Up, right? Now, if my fixed effects didn't capture much, I could see it go down. So really the answer should be that when I include fixed effects, just like a lot of other things in economics, what would happen to my adjusted R squared? The answer would be, we have supply and demand changes at the same time. Sometimes the answer is indeterminate, right? So I really don't know what's going to happen to my adjusted R squared. So I know my R squared will go up, right? Because I'm just including more right-hand side variables. But my adjusted R squared, I can't determine, right? Could go up, could go down. It depends on how explanatory those fixed effects were, right? Because I know by including them, they will increase K and therefore decrease my adjusted R squared, right? But I don't know really how much they're going to increase that proportion that I can, or said differently, can't explain. Does that make sense what I'm going through here? I tried to use colors and size of arrows here to kind of get at that idea. You okay with that? Okay. So the second question. Okay, so we know that our R squared will go up. We can't say for our adjusted R squared. Let's assume instead I'm trying to predict GPA dependent on how many credit hours someone's taken. I'm doing this across every IU student, so I can get access to this data. One thing I didn't mention last class, but we should have been able to hopefully come to the conclusion on our own if we think about this a little bit, is if I use the first difference approach. Remember, I introduced this idea of panel data saying what you could do is instead of using fixed effects, if I take 2021 and I subtract 2020, anything that's constant across the individual that would be the same in both years, it would get dropped, right? So it's essentially like I'm controlling for the individual fixed effects. There's one problem with this, right? So if I think about instead using a first difference approach, if by doing that, my Y variable now is person I in say 2020 minus person I in 2021. And whatever my X variable is, I think here I had GPA and credit hours. So 2022 minus I in 2021. Let's say my years of observations go from 2021 to 2024. Well, over 2024, I can subtract 2023. For 2023, I can subtract 2021. For 2022, I can subtract 2021. What about for 2021? That's where my data begins. Can I find the first difference for that first year? No. So when I run this first difference, what am I losing? All of my 2021 observations. If I instead run this fixed effects, I'm leaving out some of this stuff just to here. I'll be more technically correct here. Got our constant, got our coefficient, time period t, and then we had all those dummy variables, right? Those fixed effects. Well, here, I don't need to subtract the previous year. So what observations am I going to lose? None of them, right? So if the number of observations is lower from that first difference regression, what's going to happen to that coefficient estimate, right, on whether or not credit hours impacts GPA? Well, we showed last class using first differences and fixed effects should produce the exact same result, right? So I should still see the same size coefficient. So beta 1 from both these regressions wouldn't change. But within our standard error, we have this is like minimizing the sum of the square errors over n minus 1. So for a first difference regression, what's happening to n? It's going down. So what's going to happen to my standard error? If I divide by a smaller number, it's going to go up. What's going to happen to my test statistic? Dividing by a larger number, it's going to decrease. What's that going to do at this point? We shouldn't even have to draw this out. Smaller test statistic, what's going to happen to my p-value? Increase, which means it's going to be less likely I can reject the null. All right. So one advantage of using this first difference approach is I don't lose observations. And that's really important if I already have a pretty small data set. Right. So when I'm thinking about this question, right, the coefficient estimate, we're looking for which one's not true. Well, my estimate will be the same size. That numerator for my test statistic, that coefficient estimate, the first difference in fixed effects should give me the same value. Okay. The problem is, what is it going to do to my standard errors when I lose observations using that first difference approach? Losing observations is going to increase my standard errors. When my standard errors increase, I left out a step here. What's going to happen to our test statistic? It goes down, so my p-values will be higher. These should be true. Okay. Which of the following is kind of not true? The interpretation of my coefficient. Oh, sorry. The coefficient of my, or the interpretation of my coefficient estimate is exactly the same. Right? Well, how would I interpret these coefficient estimates? Right? It's going to be the change in here credit hours, the impact on GPA, holding all else constant. Right? So if I'm thinking which of, did I skip one here? Estimate's the same size. Standard error, the higher, p-value should be higher. Interpretation for my coefficient estimate will be exactly the same. Well, I meant to write one of these different because what should be true about all these? They're all true, right? So let's look in the back end. What did I mean to have this? I probably meant for the p-value to be smaller. And I wrote this quickly yesterday. I'm going to add in that because I wanted to review it. So let's see what I did here. I think I had that last one kind of set to be true, right? Here, the interpretation will be a little bit different, right? Because why? If I'm looking at a first difference, it's the change in X over the change in Y. Although I'm still holding constant factors on the right-hand side, the interpretation is now the change in that number of credit hours I see for that student. So it still gives me the effect of a 1 unit change in credit hours, but it's going to be holding constant everything in that regression, right? But I'm not really including controls for the individuals, right? Now, what I meant for this to be is that the interpretation would be exactly the same. It, in fact, is exactly the same, right? The only difference is that I'm making that statement off of a smaller number of observations. So if I'm making that statement off a smaller number of observations and I'm losing a year, what might be threatened? What type of validity?
Confidence, maybe.
Could be my confidence intervals, but in terms of just the interpretation, maybe it's the same value, but I'm making it based off of fewer time periods. I might not have as much external validity. So technically, I wouldn't ask a question like this. The interpretation, the way that we would just interpret a coefficient would be the same. But it's really that interpretation comes from a smaller number of years. So it doesn't have the same external validity as when I am using fixed effects. Okay? I probably wouldn't push it quite that far, but just to kind of think through these things, the interpretation of my coefficient would still be 1 unit change in credit hours would cause the predicted GPA to go up or down by whatever that coefficient is, holding the individual effects constant. So that interpretation is still the same. But in terms of our external validity, technically we're only making that statement now based off of, in my example earlier, 3 years instead of 4. Because that first year I have nothing to take the first difference of. Okay. On an exam, I wouldn't ask you something that's quite that in depth, but I did want to kind of touch on this idea that yes, the coefficient interpretation is the same, but it's from a smaller number of years. So what is threatened is our external validity. Right. And we wouldn't usually add this onto our interpretation. So if I ask you on a problem set or a quiz, you wouldn't have to say like holding all else constant for the years of, right? But in practice, right, even though the interpretation of that coefficient would be the same, it would be coming from a smaller number of years, which is a slightly different statement. Right? So if we want to be technical, this one would not be true. But if I was asking you the extent to which we have talked about things, technically all 4 of these would be true. So I wanted to kind of make that point in this question that really what is the difference between first differences and fixed effects? We're losing that first year of data.
Because the coefficient estimates are the same, however, one has a inflated standard error, that mean that one has to have wider confidence interval.
Yep, we could combine this with things we've already talked about, right? So just like it's going to impact the test statistic, how do I calculate a confidence interval? So you'll have this on that formula sheet. We're adding and subtracting whatever level of confidence we want to build, right? So this was like, if I wanted 95%, it would give me 0.025 on each side. And that's how I found that number of standard deviations to go to the left and the right. I then multiplied that by the standard error of that coefficient. Well, we said this standard error, part that we're really focusing on here, is that n-1. So the fact that first difference is we lose observations, we said that's going to increase my standard error. So that should do what to my confidence interval? Make it wider.
So that means the interpretation is like with slightly less accuracy.
Our actual interpretation of these coefficients is actually in its, how do I want to say this? The interpretation of the coefficient is, I don't want to say not related, but it's independent of its statistical significance, right? Even if we don't have statistical significance, we still interpret these coefficients the exact same way. So this is from like a log-log model. We would say a 1% increase in X causes Y to go up or down by beta 1%. That's the interpretation is the same. Now, whether or not that's a statistically significant result, that's a separate thing entirely, right? Then we actually need to look at that p-value and see, can we say that it's statistically significantly different from 0 at 90, 95, 99% levels, right? If we can't, if we fail the statistical significance, we still interpret it the same way, but technically we can't say that it's any different from. So if I fail to reject the null is, we always start out assuming that these coefficients are equal to 0. So if I fail to reject that, I interpret the coefficient the same way, but technically I can't say that it's any different from a 0 effect. So we're kind of tying in some of this stuff to stuff we've already talked about in the past. Good question. Any other questions on this? Hopefully, I think I had it set to be 2:45. Does everybody have it submitted here? We got our answers correct in. So we should be good. I'll go in here and maybe update it to like be 2:47 or something. So if we're all getting submitted, if it for some reason treats yours as late after class, I'll go and adjust the time. So kind of gives a little bit of buffer and doesn't treat those as late. Okay. Any questions on these before we kind of go to some new stuff? I shouldn't say this was somewhat new. I'm using this as kind of introduce some ideas, but also do some review. Okay. All right. So what we didn't talk about last class is an issue that we can run into when we run these fixed effects regressions. Okay. So one of the assumptions that we had, got my slides pulled open, but let's think about it this way. And I'm just going to put a year here just so we can kind of have something to think about. So if I looked at here, all this dummy variable person one. For every observation, well, I didn't want to do 20. What am I doing here? Sorry. You should all be in the same time period. If I have an observation from 2020, when I run my fixed effects model, this is essentially what it's treating as. There will be an error term associated with the year 2000 here for that individual. The fact that I included a dummy variable that controls for that individual, though, what is likely true about the error that could exist for every individual across time? So even though I've controlled for the individual, that error term in 2020 could be very different from the error term in 2019. However, these time invariant factors are going to be correlated with the errors in both years, right? For any one individual, when I make a prediction for them, the amount that I'm going to be off might be the same for that individual across multiple periods in time, in which case these error terms would be correlated with one of my controls. What is one of the assumptions that we kind of had was that the expected value of my error term for different values of my controls was equal to 0. Well, if some of my controls now, the error in time period t-1 is likely correlated within the same individual with their error from 2020, right? I'm likely to be making similar errors for the same individual across time. Well, now this is likely not going to be true, right? And this is a direct result of the fact that the control I'm using is not just from 2020. It includes, I don't know, kind of think about it, a whole bunch of different time periods. So essentially what we want to know, if this is going to not happen, so in order for us to make sure that our expected value of the error term, given this different values for X, given these new dummy variables we've included, fixed effects, the way that we kind of need to guarantee that this is equal to 0, it's not quite clear. We won't work through the math as to why, but what we need to be true is that the correlation or the expected value of the error term from this period and the previous period, that it's different than negative 0.5. Once again, we won't walk through the math as to why, but you can kind of imagine, like, because we're likely to have the same correlation of those error terms, we want to make sure that it's different from, you probably, if you just had to guess, you would assume we would test to see if it's different from 0. The mathematics actually works out to be that it needs to be different than negative 0.5. That's because if I think about plugging this in, this would be like subtracting. If I think about more like a first difference thing, that's kind of where it comes from. We're not going to walk through the mathematical proof as to why, but this is what we need to be true in order for us to make sure that the expected value of the error term given the different X values is equal to 0, to make sure that that assumption isn't violated. Okay. So what are we going to do? All right. So slideshow here, if this will. Did I lose this? Yep. Spinning wheel adapt here, so hopefully this doesn't last too long. I'll just start working through it instead of doing it in bullet point form, I guess. So we need this correlation of our error terms to be something other than negative 0.5. There we go. Okay. So in order for this assumption not to be violated, we need for this to be true. So one thing that we talked about with errors, what was an adjustment we could make when we thought that there might be heteroscedasticity? We talked about robust standard errors, right? So that's seems like maybe a solution to this, but it's not going to quite correct for that autocorrelation if we're looking at panel data. So just simply using the robust command won't solve our error problem like it did before. Okay? So what we're going to do is we start out assuming there is no autocorrelation. Okay? So we'll start out assuming that there was autocorrelation. This would be not equal to negative 0.5. We'll start assuming that there is no, so we're assuming it's equal to negative 0.5. We'll kind of walk through the steps to test for this, right? I think I've got them kind of written down here, but I think it'll be easier once we work through a couple examples in Stata. But we're going to run a first difference regression, right? We're then going to obtain the residuals from that first difference regression. So you can kind of think about what are we doing? We're taking time period t minus 1. We'll then look at that error term. That will tell us something about the correlation of the error term from time period t and t minus 1. Okay. We're going to do something called cluster our standard errors, right? Once we have these residuals, we're going to run a regression of these residuals on the lagged residuals. So all a lag means is if I'm looking at the difference from 2020 to 2019, the lag would be the difference between 2019 and 2018. So just going back one time period. When we run this regression, we're going to then test to see, is that coefficient not different from 0 like we do in every other normal regression? We need to know are those error terms, is the correlation any different from negative 0.5? So instead of testing against 0, we're going to have to add some things into Stata so it'll test it against the value of negative 0.5. And then if we can say that it is statistically different, we have autocorrelation. If it's not, but I can't say it's any different than negative 0.5, we don't have to worry about this autocorrelation. Okay? So what is this going to look like, right? I think it'll make a little more sense when we kind of walk through an example in Stata. So I'm going to set my global path here, that panel data post file that I have up there. We'll scroll down. Where were we at last class? Looks like, here we go. I'm going to use that GDP class data. Okay. So we did some of this last class. We're going to kind of come down here. Here was our kind of regression with our fixed, whoops, what did I not create? I didn't create this, right? So we created those kind of unique state county identifiers. We ran that fixed effects regression. I see my coefficient estimate. Now, my coefficient estimate won't be impacted by autocorrelation of my error term. What will be impacted, just like when we had heteroscedasticity, we said the coefficient value will be the same, but my standard errors are going to be off. So my statistical significance is going to be what I'm worried about. So I'm really worried that this p-value might not actually be 0. I mean, that seems like an egregiously large test statistic, right? So what we're going to do is the first step. So maybe if I'm kind of working through this here. Oh. My first step would be kind of calculate these differences. Well, I guess I need to come back up here. Sorry. So I'm going to calculate the differences in the two variables I was interested in, the unemployment rate and income. So once I've set this up as a panel data set, so we had this state, county, and by year data, that was our panel data set. Instead of, there's some different ways you can do this if you Google it. The easiest way is once I have it set up as a panel data, if I wanted to create the difference in the unemployment rate from the current time period and the previous, I can just take the unemployment rate and subtract L dot that same variable. So because I've already identified to state that this is a panel data set, it recognizes, look at the same state county, but take it from this year and go back one time period. That's what that L dot tells it. Lag it, right? Go back, lag it one time period. So if I were to kind of create this variable, just to kind of show you in the data what this is doing. Oh, I didn't want that. There we go. For Pendleton, Kentucky, right? Well, can I find the difference from the very first year in my data set? No, I don't have 2010. So when we're looking at these first differences, we said we lose the first year of data. But for 2012, when I created that unemployment difference variable, it took the unemployment rate in 2012 and subtracted the unemployment rate for that same county in 2011, giving me that value of -2. And it went through and did this for every single county. Notice every time I look at a new county, that first year, I can't calculate the difference, right? There's just a missing value there. Is that making sense what state is doing there? So I'm going to do the exact same thing, but I'm going to do this for the income variable as well, right? My X and my Y variable. So I'm now looking here. I've got my differences created. I'm going to run that first difference regression. So I'll come back to this. I just wanted to remind myself to do this. So step 2 is I'm now going to run that first difference regression. Okay. So I'm now looking at the unemployment rate difference and the income difference. Same variables I ran in my fixed effects regression, but I'm using the first difference approach. What I'm then going to do is use that predict command to obtain the residuals from that regression. So when I look at that first difference, right, it's going to basically calculate what that error term is, save it for every single observation. So I'll run that first difference regression, and I'll kind of combine it and save the residuals, right? So Stata runs that regression. Notices all those missing values, so it can't use those observations. But in the actual data, what did it do? For every observation where it had those differences, it calculated that error term for that observation. Once I have those residuals, I'm going to run a regression where I look at those residuals and I run a regression with those and the lagged residual terms. So it's like take the errors that were made in 2020, run the regression on the residuals or the errors that were made in the 2019 observations. Now, what I need to make sure I do here is include this no constant. So when we run this regression, we said we were just looking for a correlation, right? So if I run a regression, this kind of gets weird. It would go back a bit. If I just run a regression without a constant, I won't have like a line of best fit. There's no starting point. So really all I'm doing is picking up what the correlation coefficient is, right? So that's kind of going back to even more basic statistics. Now, we also need to make sure we include this thing called clustering of our standard errors, right? So clustering of our standard errors says, look at these residuals across time, but identify that different states and counties are going to have different errors that are consistent across time. So some county in Kentucky will have errors that are consistent across the time period that look very different than some county in, around New York City. Right? So that's what that cluster command does. It accounts for that there might be variation in those error terms within the same subject or the same state county here. But it still is looking for, is there autocorrelation in the errors from time period 2020 and time period 2019? So we're just looking to see if there's error correlation, not within the same subject, the same state county, but is there autocorrelation across time? That's what that clustering does, is ensure we're just looking at time. Once I run that regression, the fourth and final step, test to see if it's not 5, if it's different than -0.5. When we start out assuming that there is no autocorrelation, what that correlation should be is -0.5. So if there is autocorrelation, it will be something that is different from -0.5. That's what our fourth step is, right? We're not testing to see is it different from 0. If there is autocorrelation, it will be different than -0.5.
To be in a certain range outside of 0.5, or is it just one?
So let's think about this, right? What am I running here? I'm running a regression. If I were to run a simple linear regression, not thinking about this, what do I assume the coefficient is equal to? I could still see a value for the coefficient. And how do I determine if I can say it's different from 0? I look at the p-value, right? Even though any regression we run, we're going to see a coefficient estimate. But if it's not statistically significant, we can't say that it's any different from 0. Here, the value of negative 0.5 essentially is saying we have no autocorrelation. We're going to see values that are different from negative 0.5. Whether or not we can say it's statistically significantly different from negative 0.5 will be based off the p-value we get from this regression on that lagged residual variable, right? So when I go ahead, I've already kind of calculated these differences. I predicted the residuals. I think I ran that code already, right? Yeah, we already did that. If I then run step 3, where I run the regression of the residuals on the lagged residuals, okay, I have a coefficient that's different from negative 0.5. But can I say that it's statistically different or significantly different from negative 0.5? Very strong. The p-value is 0. Now, if I saw like 0.11, and notice here, why do I probably have a lot of statistical significance? Number of observations is really high. Let's say I ran the same thing, but I only had like 400 observations. I could still see the same coefficient value here of 0.11. It's different than negative 0.5, but could I say that it's statistically significantly different from, or the statistical significance would be different, right? Is it different from negative 0.5? My p-value might be a lot higher there. So I could see the same value from a small number of observations, even though it's different than negative 0.5, I might not be able to say this at the 90, 95, 99% levels. Okay? So we'll look at a couple more examples here to kind of get through on this. But at least in this case, I can reject the null, or I can reject this test that it's different from negative 0.5, right? Or sorry, I didn't complete this yet. I explained it, but I forgot to run the 4th line of code. This is our regression. Now, this p-value from the regression is actually testing against what value? Every regression we run, I said, we assume the coefficient is equal to 0. So this is it statistically different from 0? If I want to know, is it statistically different from negative 0.5, that was where our 4th step came in, which I thought I already ran, but I didn't click it, right? So I run the regression. I then say, test it not against 0, test to see if it's different from negative 0.5. So there, notice I get a slightly different p-value. I mean, it's 0, but my test statistic, I guess this is an F distribution, so it's going to be a little bit different. But I might see different values here. This happens to be a case where both of them are 0 because it was pretty far from negative 0.5, right? But it could be different from negative 0.5 and not different from 0 or vice versa, right? It kind of just depends on the directional, like what the sign was and what my right? If I could say that it's, let's say I saw negative 0.2, I might be able to say that's different from 0, but not different from negative 0.5, right? It's closer to 0 than negative 0.5. So the 4th step, the p-value we actually want to look at is when we test to see not is it different from 0, but is it different from negative 0.5, right? Now, in this case, I actually could say I know which one of these p-values is smaller. So think about what we're doing when we create these test statistics for coefficients to find our p-values. What we're technically doing is we're saying, I have this assumed true coefficient. I have this assumed true coefficient. Here's my prediction. Divide that by kind of my standard error. Well, from our usual regression, it's testing to see is this different from 0. When I saw a coefficient estimate of 0.11, and I see that the p-value was like, or 0.0000. When I actually test this against negative 0.5, the only thing I'm changing, I have the same coefficient estimate, I have the same standard error, I'm just changing this to colors here. Negative 0.5. Is this distance going to be greater or smaller? This is 0.11. The difference from 0 would be 0.11. I test against negative 0.5, the difference would be 0.65. So my test statistic, when I test it against negative 0.5, is going to be higher, which means I know that that p-value is actually going to be lower. Okay? I wouldn't push you that far in terms of asking you those types of questions, right? In terms of identifying autocorrelation, you're going to want to look at the p-value of that test command where you test it against negative 0.5. But in this case, I mean, if it's different from 0, it definitely has to be even more different from negative 0.5. Questions on that idea? So here, do I have evidence that there's autocorrelation? Well, I'm rejecting the null. The null is that we have no autocorrelation. So yes, I reject. This is going to be kind of a weird one. If I assume there's no autocorrelation, if I'm rejecting that, what I'm actually saying is that there is autocorrelation. Right? So here I have a concern. I think there's autocorrelation in my error terms. So what do I do? So this is kind of our test. What we would want to do is in our regression, right? And here I can kind of think about, I did this by year. I'll kind of show you a different way of looking at this in a second. But let's say, excuse me, I run this regression. What is this actually doing? It's kind of, I set this up with I dot. Well, we said I dot is really just a different way of using what type of fixed effects here. If I do I dot year, I'm using year fixed effects, right? So if I run this same regression, but I then include this command VCE cluster by the state and county. What this will do, excuse me, is account for that autocorrelation, right? It will adjust my standard errors just like the robust command did. It's just that the robust command was dealing with heteroscedasticity. This VCE cluster, this will deal with the autocorrelation issue. So when I run these two regressions, I should hopefully see the exact same coefficient estimate. But notice what happened to my p-value. It changed by quite a bit, right? So once we account for this autocorrelation, we'll see the same coefficient. We'll have the same interpretation of that coefficient, but its statistical significance might now vary. Might be higher, might be lower. We don't really know, right? To kind of just make this point even further, I could do a similar thing. Instead of year fixed effects, okay, let's say I do here. If I've set this up with my xt set command state, county, and year, we said when we use the FE command, it includes fixed effects for whatever the subject is, whatever that first thing that I set the panel data set up as was. So here it's going to include fixed effects for the state and county. So if I do the same thing down here, instead of using year fixed effects, I'm now using state county fixed effects, but I'm still using that cluster command. I'm still going to adjust for this autocorrelation. So even with different fixed effects, adjusting for that autocorrelation, what do I see the sign of my coefficient now become? Well, I'm using different fixed effects, so that number is different than before. But in terms of just running this new regression without that cluster command versus running it with, if I just looked at the p-value, could I say there's any difference? Well, they both look like it's 0. But which of these is statistically more significant? When I did account for the autocorrelation, or sorry, when I did not include, when I did not adjust for the autocorrelation, or when I did? Well, if the test statistic is smaller in absolute value, even though I can't see it, I know my p-value here must be, test statistic is smaller, I know my p-value must be higher, there is less statistical significance. Okay. So in some of these examples, you might not be able to identify it based off of the p-value from that output, but looking to see once I clustered those standard errors and accounted for that autocorrelation, I can use the test statistic if it's not clear out to the third decimal. Right? Whichever has a smaller test statistic, I know has to have a larger p-value or less statistical significance. Okay. Any questions on this before we keep moving? Yeah.
Can you go back over how you got the fixed effect variable or how?
Up here from what we did last class?
Yes.
Yeah, so what we did was by every state and county, we created this unique number which identified the very first observation for every state and county. So if I go back all the way here, oops. Why isn't it like this? Up there earlier, what error is it telling me? User. Here. I think maybe I move things around. So let's set my global. Let's come down here. Yeah, there we go. We'll open up that GDP class data. So what I did was by every state and county, I created this unique identifier, which we said for every state and county, the first year of observation, it just put a 1. Then when I sorted by this unique variable, and then for every time there was a 1, I created a new state county ID that didn't exist before, and underscore n said, take the very first state county, give it a 1, take the second state county, give it a 2, so on and so forth. So when I ran that line of code, I can now see that Livingston, New York, I gotta scroll down. Where are my 1s? All the way down here. There we go. So what? Menard, Texas, that was state county number 1. Cumberland, Illinois, state county 2, so on and so forth. Well, that only did that for the first year of observations. So the third thing I did was I said, by each one of those state and county IDs, right, that we created, I'm going to then put in the maximum value of that state county ID. What that will now do is now every time Care Texas, it's not just the first year that has the 1709, it's every year gets that. And now this I can use in my regression as my fixed effects, because we couldn't use names, we couldn't use text, we had to create this kind of unique identifier. Like, give you something like this or a problem set, I would likely give that. I wouldn't make you create these. I was just kind of showing you that you can. I would probably give you already something that has a unique state county ID, right? But then once we have that, we just set our panel data set up by that state county ID number and then year, and then that's our panel data. That's when we can start using these lag commands. Is that what your question was?
Yeah.
The other questions on this example before we look at one more example of autocorrelation here. So the next thing I have, we're going to open up this fatality data set. So we've got that opened up. And I wanted to run this weird regression where I was like, I wonder if beer taxes, right? What would beer tax do? Increases the price. So people should consume less, which means there might be fewer traffic fatalities. So maybe mortality rates go down. I mean, this is like right? I'm kind of thinking through this pretty far, and maybe that effect is minimal, but it might exist, right? So I run this regression, very naive, because what is likely true, right? States with different beer taxes, those taxes are likely kind of going to be higher in some states than others. I haven't controlled for what that state is. And certain states that are more likely to pass beer taxes, well, maybe if I'm not making money off of a marijuana tax, maybe I increase beer taxes more. Well, the fact that I don't have marijuana legalized, I can't tax it. Now I'm looking at two very different states. This is omitted variable bias, like going to be huge, right? So this is a very naive regression, but it looks like, okay, it's not statistically significant, but the higher the beer tax actually looks like it's increasing mortality. So it went against my kind of intuition, but there's a lot of omitted variable bias here, right? So what I'm going to do is set this up as a panel data set. I've got different states across several periods in time. Okay? So I'm going to say, set this up as a panel data set. So if I look at this data, I've got Alabama for what, 82 to 88, right? So this is kind of an older data set. So I set this up as a panel data set by state and year. I'm then going to run my fixed effects regression. So what fixed effects or what dummy variables would this regression include? A dummy variable for every single, said that fixed effects will be the first variable. So it's going to include fixed effects for every single state minus 1. It's going to leave 1 out. It's essentially what we're doing before with categorical variables. So if I now account for things that are time invariant within a state, right? So this is a lot of things that I can't observe. This is differences in the states, maybe not, we're not looking at beer taxes, but maybe their policies on, like I said, legalized marijuana. Maybe this is looking at whether or not they have the death penalty. That might impact mortality. Whether or not they have subsidized healthcare programs, that's going to impact mortality. All of those things that are likely to be consistent within that state across time, I'm now controlling for. And now the estimate I get is no longer positive, but negative and much larger in magnitude, right? And it's statistically significant. So now this lines up more with what I was thinking. beer taxes might decrease consumption, holding everything else constant that is time invariant within a state. Now it looks like higher beer taxes will actually lower mortality rates. So maybe the state would be like, yeah, we're doing you guys a favor, right? We're increasing beer taxes, we're lowering deaths, right? Now, what if we think that could be autocorrelation, right? That things that are impacting mortality in time period 2020 are likely going to be impacting mortality rates in 2019, right? So what we're going to do, we'll kind of walk through this again. So step one is create and run that first difference regression, right? So I'm going to show you a slightly easier way to do this. I mean, it's not that much easier, but I used the LDOT command earlier to lag the variable. If I ever use, once I have this set up as a panel data set, the DDOT command does the same thing. It takes mortality rates in time period T and it subtracts the lagged mortality rate. It's just I don't have as much typing to do. Right? So it's going to do the exact same thing as when we took the current variable and subtracted the lag. It's just that because I'm telling it DDOT, it identifies I can do all this behind the scenes. So it does the exact same thing, right? So that DDOT command is just kind of saving me a little bit of time, right? It's calculating that difference, between time period T and the lagged time period, right? In fact, I could prove this to myself, or I could prove this to you. I guess I don't really need to prove this to myself, but because I don't care. I know that I know. So let's do 2, and we'll say take all mortality and subtract all mortality. I have to put the LDOT command in front. If I create both of these, hopefully I get the exact same values. It's just an easier way of calculating that difference, okay? So I'm also going to do the same thing for my X variable, beer tax, create that first difference. And then I'm going to run that regression of the difference in mortality on the difference in beer tax, that first difference regression. Now, once I do that, step 2 was I need to save those residuals, right? So I'm going to run that first difference regression. I'm going to use that predict command. So this is where I typed things out before. There's actually some shorthand we can use. So before, when I ran that first difference regression, this is where there's like 2 ways to skin a cat. If I do predict and I call this new variable the residuals, and then I put comma residuals, if I shorthand that with an R, it knows to create the residuals, but I don't have to type out the whole word here, right? It does the exact same thing. So it's just a slightly different variation in code. It's like saying yeah instead of yes, right? It's just can identify this, okay? So I run this first difference regression. I predict the residuals, right? So we run that regression. We save those predicted residuals. We now have those in our data set. Remember, we said because we use the first difference approach, we won't have those residuals for the first year. So if I've done this correctly, hopefully for the first year of every single state, I've got a missing value, right? Because there shouldn't have been anything to take a difference from, right? There's no prior year. So then step 3 is regress those residuals on, if I can spell, the lagged residuals. Now, here's where we had to do a couple things that were not like we usually do when we run a regression. So I've now got my residuals. I run that regression trying to predict them with my lagged residuals. We said in these regressions, because we just want to know is the correlation different than negative 0.5, I don't want to include a constant. I'm not really estimating a line of best fit. I'm just estimating a correlation coefficient. So I include that no constant command, right? And then I also have to cluster at whatever level I'm eventually going to want to include my fixed effects for, which was the state. And that was our original regression where we had fixed effects from the state, but we said, okay, this coefficient might be right, but our statistical significance might be wrong because of autocorrelation. Is there autocorrelation? Now we're going to test for this, right? So I run that regression. Now at this point, I have one more step. I don't want to stop here. Does this value look like it's different from negative 0.5? Yes. But how far away would this be from negative 0.5? negative 0.8-ish. I'm rounding pretty egregiously. How far away would this be from zero? Negative 0.12. That's what that p-value is testing for. That's testing to see is it different from zero. We actually want to test to see is it different than negative 0.5, which is why we have the fourth and final step, which is test to see if it's any different from negative 0.5. That regression result just showed us, is it different from zero? That's not, I shouldn't say it's useless to us, but it doesn't tell us if there's autocorrelation, right? So we then need to run this test command to see, is it different than negative 0.5, right? And just to kind of make the point here, I mean, so in this case, it's going to be further away from negative 0.5 than it is from zero. So those, even though I have a p-value here of 0.004, my p-value might even be smaller, right? And if this was instead like negative 0.4, well, that would be closer to negative 0.5 than it is to zero. So those p-values from the regression don't tell me anything. I need to actually run the test to see is it different not from zero, but is it different from negative 0.5, right? So I run that regression. Sure enough, I get a p-value here that's even closer to zero, right? It's not 0.004, it's 0.0000 out to the fourth decimal. So I have a result here that's highly statistically significant. So just like with linear regression, we start out assuming there is no effect. If we can reject that, we're saying there is a statistically significant effect. With autocorrelation, we start out assuming that there is no autocorrelation, which is a good thing. That's what we want. If we can reject that, p-values less than alpha at any level, we're rejecting that there's no autocorrelation, so we found evidence that there is autocorrelation. We need to now adjust for that. How do we do that? It's really pretty simple in Stata. We don't have to worry too much about this. I just run that fixed effects regression that we had up here. So I'm gonna just copy and paste this so we can compare them kind of back to back. All I have to do is include this VCE command, and I cluster my standard errors at whatever that subject level is. Whatever I'm wanting to include fixed effects for, in this case, the state, I cluster my standard errors at that level that adjusts for this autocorrelation, okay? I think in our earlier example, when we adjusted for it, it actually caused our significance to be a little bit smaller, right? Our test statistic went down. We'll see if that's the case here, right? So I run my regression without adjustment, run my regression with the adjustment. In this example, so I see the exact same coefficient size. Autocorrelation does not impact the size of my coefficient. It will still be unbiased, but it could impact the statistical significance. In this example, what happened is it became less statistically significant. Now this one I can see, right? P-value went from 0 to 0.007. So you can imagine a different example where if it increased that p-value enough, we might go from without clustering our standard errors, finding statistical significance, to once we cluster and account for that autocorrelation, our result now becomes statistically insignificant. It wasn't quite that bad in this case, right? It's still significant at all of our conventional levels, but it does push that p-value up, right? Now the two examples we had just happen to be examples where it lowered the statistical significance. It is theoretically possible. So if you're looking at a quiz question or the problem set, depending on the data, when you account for the autocorrelation, depending on which direction it goes, you could actually see not just less statistical significance, you could actually see more. We don't know. We know that it will change the statistical significance. We just don't know in which direction. And let me save this real quick before I forget, because I'll post this since I kind of added in the steps, because this might be helpful when you are working on that sixth problem set to kind of have in the code like what the steps to this autocorrelation were, right? And you have two examples. I did things slightly different in the second example. I showed you some things that were like a little bit more shorthand or kind of shortcuts, but really either approach would be counted as correct. It's just different ways of doing the same thing. Okay. Any questions over anything that we have here?
So you said that the null hypothesis for this is that there is no autocorrelation between the variables?
Not between the variables. What was autocorrelation between the error terms, right? So maybe to kind of summarize it. Our null is no autocorrelation. Another way of saying that more using actual statistics is that the correlation of our error term from time period t and time period t minus 1, if there is no autocorrelation, this value should be equal to negative 0.5. So when we're running this regression testing for this to see, we assume there is no autocorrelation. Do we find evidence that there is? Can we reject this? Well, then what we're looking for is when we eventually get to that fourth step and we're seeing that test command to see, is it different from negative 0.5? That p-value is going to allow us to either reject or not reject the null. If we reject the null, that means we saw a correlation that was a lot different from negative 0.5, right? At statistically significant levels. And then we're rejecting that there is no autocorrelation, or if we're rejecting that, we're really saying we found evidence that there is autocorrelation. It's kind of, like I said, the same as a linear regression. We really start out assuming there is no effect. We reject that, we're saying that we found an effect. We start out assuming there is no autocorrelation. If we reject that, we are saying that there is. It's just now rejecting is kind of a bad thing, because like before with the simple linear regression, rejecting, we were saying, no, we found that there is an effect. Here, when we reject, we're saying, oh no, there is autocorrelation. I know my p-values are messed up. I need to adjust for this, right? So this kind of identifies now, oh, I have one more step to do, which is cluster my standard errors. If we had an example where I fail to reject, well, if I fail to reject this, what is there? No autocorrelation. So do I need to use that cluster command? No. Right? It shouldn't influence my statistical significance at all if I fail to reject this test.
Could you explain why it's bad to have autocorrelation again?
Because essentially, what did we want? We wanted the expected value of our error terms given different values for x to be equal to 0. That was the assumption that if I took out time periods, heteroscedasticity violated. That was an issue that we talked about. We could use that robust command to account for. It's kind of sneakily hidden in here, but one of the controls we're using is a fixed effect. So what is likely going to be true? In Alabama, the error I make in 2020 is likely going to be correlated with the error that I make in Alabama in 2019, which is likely to be correlated with the error I make in 2020, 19, 18, right? So these time invariant factors within the same state, well, it's likely that my error term, if I'm using the state as an initial control, what does this really capture? This is capturing the time or the error terms from earlier time periods, which would say the correlation of my error with previous time periods is not equal to 0. So if this was not equal to 0, we're violating that assumption that we had way back a long time ago, simple linear regression. So it's kind of the same assumption is being violated as when we had heteroscedasticity. There's just a different way to account for it with a panel data set, which is to cluster those standard errors at the state level. So this isn't technically quite correct, but maybe a good way to think about this. When we cluster those errors at the state level, it's essentially like we're taking the average error we're making within that state across all time periods. So if we kind of take that out, now our error term in any one time period, we've taken out the average error in that state. So now it shouldn't be correlated with any other. Now our assumption isn't violated. That's not technically quite correct, but it's one way to think about it. When we adjust for that autocorrelation, we're essentially like taking out the fact that within that state, the error terms kind of have like an average, right? That every single time period, the errors we're making within that state are going to be similar. We're kind of taking that out by clustering the state. We're taking out like that average error within that state. It's not, once again, technically quite correct, but that's a good way, I think, to think about it.
All right, so to get this straight, it's taking out the time invariant error per state in this case.
I don't want to confuse you too much, but it's a way to think about it is it's taking out. I would say the way to think about it is it's taking out the average error across time within that state. Okay? Is that it's similar, but it's a little bit different, right? Like it's
To show which year deviates from the average most. Yeah, okay.
so it's slightly different way. Once again, that's not quite technically correct. If we're talking about the mathematics, we would want to be a little bit more precise in the way that we are saying this. But for the sake of what we're doing, we don't even really need to know any question I'd ask you. You don't really need to know why that works. We just need to know by clustering those standard errors, we are removing that autocorrelation. And then we're back to having not this assumption violated. This goes back to now being equal to 0 and we're okay. Any other questions on anything here? All right, so kind of went a little bit longer than what I had planned on. But that should kind of get us through this file. We talked through all the slides for this week. I would start to review. And once again, I know it's break. I'm not telling you to work over break or anything like that. But I would, once we get back, even before we kind of go over the next topic, which will be instrumental variables, start to review this fixed effect stuff using like the first half of these sample questions. This will get you a good idea of what the types of questions you'll see. And then that 6 problem set, if you do want to start working on it, I'll post it tomorrow. About that first half of that problem set will be related to kind of the stuff that we've been doing in this do file this week. Okay. Do have time tomorrow or early in break to work on it. Maybe it's good so you're not like super far removed from it. And it's always kind of a tough thing. Any other questions just logistically for me before I kind of let you guys do that? So I appreciate all of you showing up. I know that like Thursday before Thanksgiving break is usually low attendance, leave early, which you guys should feel fortunate. Where I was here, a lot of schools, they only have Wednesday, Thursday, Friday off, and they still would have had class on Tuesday. So when people are like in a huge hurry to get out of here, I'm like, there's a lot of universities where like you would still have to go to class next week, at least one day. You can imagine what attendance looks like then. But I appreciate you guys for hanging around. I think it'll kind of help you approaching this problem set. Next quiz. Other than that, have a fun, safe Thanksgiving break. And I will see you guys on Tuesday after break.